morning, everybody. Thanks. Nice to see you, everybody. Smiling faces. Thank you, Ron, for the introduction. So, ecosystem services are nature provide us many things: food, clean air, water, material for industry, medicine, and buildings. Those are called provisioning services because ecosystem services are divided into 4 different categories: provisioning, regulating, cultural, and support services. Regulating services include flood control, clean air, clean water. Then supporting services, biodiversity, soil formation, and photosynthesis, that is increasing productivity of cropland. So I'm going to talk about a couple of those points and how agroforestry can improve these services. So we need these services because well-being of the human being and quality of life. But some of these ecosystems have been impacted by some anthropogenic activities. That means the services we are receiving from ecosystems decline. So I am going to talk about how agroforestry can improve those services. So as you first, our first topic is about water quality. So water quality is not a regional problem, it's a global problem. As you know, water quality is impacted by anthropogenic activities. So in Europe, these red areas represent highly impacted areas. And in the US also, as you see those red areas and yellow areas, each red dot represents 5,000 acres of highly eroded soils, that is HEL, HEL. Then the yellow dot is 5,000 acres of non-highly eroded soils. Total is about 57 million acres red, 157 million acres yellow. So recent studies have shown that the erosion estimated by soil loss equations are much smaller than the actual losses, about 3 to 40 times higher, the erosion compared to. What happens to these sediment nutrients? Finally, they enter the ocean, right, causing hypoxia conditions. If you look at the second map, you see global hypoxia conditions. In early 1900s, there were less than 10 hypoxia conditions throughout the world. Now there are over 400 hypoxia conditions. That is 400% increase on hypoxia conditions global. What causes those? We apply nutrients. We don't do good conservation practices. Those nutrients, sediment, enter the water. So we conducted 2 long-term studies to understand what are the benefits of agroforestry. One study was at Greenlee Center, Knox County. That is about 95 miles northeast of Columbia. Then the second site is at HARF, Horticulture Agroforestry Research Center, 45 miles west of Columbia. At the Greenlee Center, the study site is looking at LA cropping practices and corn soybean rotation. Each of these watersheds are instrumented with flumes, approach sections, water samplers. And the HARF site is on grazing project. So we looked at how agroforestry can improve water, soil in those management practices. Let me explain about the watershed study. That is the Greenlee Center corn soybean with LA cropping practices. As you know, watersheds, you cannot have replications. So we started a paired watershed study. Paired watershed study means we continue to monitor those 2, 3, or 4 watersheds. That means collect water samples from the beginning, analyze those samples for sediment, nitrogen, nitrate, phosphorus, dissolved phosphorus, if you are interested, herbicides, and all the parameters. Then we develop a relationship between the watersheds. So if one watershed generates X amount of runoff, cubic meters per hectare, how much is coming out of the next watershed? So we know what is the normal water runoff, sediment loss, nitrogen loss of the watersheds without any treatments. So we conducted that study for 7 years, 1991 to 1997. So then we were satisfied. We developed a very good, significant relationship among the watershed. Now we know if this watershed generates 100 cubic meters of flow, how much is coming out of the next watershed. Then we established our treatments in 1997. Now you see on the west watershed, thick gray lines that represent grass buffers. Brome, red top, and clover were in the grass buffers. On the middle watersheds, we have trees within the grass buffers. Those were pin oak, bur oak, and swamp white oak. Those were planted alternately. The idea is to remove two of the species and leave the best species for the study. So now you have very good relationships. So now we can see if there is any change in runoff, sediment, nitrogen loss that was caused by these buffer management practices. So this is just to give an idea. Trees were planted in 1997. Now they are at the site almost close to 30 years. The average height is now about 8.5 meters. They are 10 feet apart. So what we did was, as you see here, initially, the watersheds have generated more runoff because there was a lot of disturbance during tree planting. We had to dig holes. Heavy machinery was going through the site. So both watersheds, the grass buffer watershed and the agroforestry watershed, both generated more runoff, more sediment loss, more nitrogen loss during the early 6 to 8 months. Then as time progresses, those concentrations decreased, as you see here. So we have published several papers looking at surface water quality, 2002, 2011, recent publication was in 2023. So what we saw was, compared to the initial study, initial publication, water quality has improved. Initially, runoff reduction was about 11%. Nitrogen reduction was less than 15%. As you see here, now the averages are between 40 and 48%. Sediment, nitrogen, runoff, everything has gone down during the last two publications, that is 2011 and 2023. So initially very low reductions, efficiencies of filtering. As time grows, it improved from less than 20 to 45%. So which shows that agroforestry can help improve water quality, can reduce nitrogen, nitrate, phosphorus, dissolved phosphorus, and other herbicides. So my first talk section is on water, about surface water. That is runoff water that comes over the soil surface. Then I will go to talk about groundwater. Then there is another water, kind of water in between the soil surface and the surface soils. That is called shallow water. So once we have all these water quality parameters, we want to look at what are the future benefits if we continue this study. So we selected APEX program, agricultural policy environmental extender, because that we have small watershed, we have all kinds of data at high resolution. We use the APEX program. So as you see here, we have topographic data, soil data, management, precipitation data. So to run the APEX program, so these are our three watersheds. Watersheds were divided into sub-areas. Each watershed had about 12 to 14 sub-areas based on the land management, crop area or tree area, grass area, soil differences, topographic differences. That's how you run the model. So we divided those and looked at the watershed for different scenarios. As you see, we have 6 buffers on the original watersheds. They are taking about 16 to 18 area of the watersheds. We looked at 5 different scenarios. 10% of the buffer area at the end of the watershed and half in the middle of the watershed. And as you see here, 2 different shapes. And the last 3 slides scenarios show all the buffers at the end of the watershed. So those were the scenarios we analyzed because we had 30 years of data. So we can do all kinds of analysis. We can replace the plant species. We can increase the buffer thickness. We can remove 1 buffer, 2 buffers, 3, 4. All those scenarios can be analyzed because we had very rich data set. So before you run the model, we want to make sure that model is doing a good job. So that includes kind of calibration and validation. During the calibration period, you fine-tune the model. So measured data and the simulated data has to be almost equal. So there are several performance indicators, R squared, P bias, Nash clip. As you see here, these lines overlap. That means we had a very good calibration and validation relationship to run the different scenarios. So we looked at those 6 scenarios. The first set of columns, that is the top part of the graph, which shows the reduction of sediment. So currently no buffers, very high sediment in the water. As you see the red block, that's the best condition. Sediment concentrations were reduced and the lower part shows phosphorus and runoff was reduced. As you can imagine, when you put a buffer in the middle of the watershed, that reduces the slope length and slope steepness. So that means capturing what is coming from the upland area and storing them in here. And that buffers at the bottom end also help to remove all the nutrients and sediment that enters the water stream. So that's why those two buffers conditions were the most efficient in terms of removing sediment, nitrogen, phosphorus from those watersheds. And Chung Ho Lin looked at effects of buffers on herbicides and antibiotics. He conducted a simulated rainfall study at the Bradford farm. He looked at, these are the 3 antibiotics used in livestock industry. They use these, if you look at the data, antibiotic users in livestock industry, they annually use about 22 million pounds of antibiotics in livestock industry. Only about 30% retain in the animal body. 70% is going to soil or water. That can disrupt human activities, wildlife, and all the living organisms in soil and water. So he wanted to study what are the effects of different kinds of buffers on reduction of antibiotic concentration in water. He looked at tall fescue, native grasses, and hedge and fescue. As you see here, when the runoff water goes through the buffer within the first 3 meters or 5 meters, the concentration drops. So that shows if you have a 10 or 15-meter wide buffer, you can remove 100% of the antibiotics coming out of watersheds. Okay, this is for the antibiotics. And similar story for herbicides. As you know, atrazine, metolachlor, and glyphosate. Those are the herbicides that use in large quantities in agricultural production. As you see here, these agroforestry kind of watersheds remove those concentrations. That reduction is different from plant species to plant species. Native grasses are much more effective, and the combinations are much better in terms of removing herbicides and antibiotics. So now I have explained about the surface water changes in agricultural watersheds as influenced by agroforestry. We wanted to study what is the effect of agroforestry on groundwater. This study was conducted at the HARF, about 45 miles west of Columbia. We installed 3 different wells. The slope of the land is about 12%, summit well, mid-slope well, and the well down the buffer. So this shows the well configuration. The summit well is about 12-meter deep, mid-slope well is about 10 meter, and the lowest landscape position next to the lake, the well is about 4-meter deep. So we drilled those wells, and wells had the screening devices. So it enters water from a specified area into the well. So we had a pump inside the well that we can take water samples. First we go to the field, empty the well because this is a standing motor. 3 or 4 times we empty the well and go to the other well and empty all the wells. Then we start collecting water samples with new water. So we sampled these wells for 2 years, every other week, and brought those water samples to the lab and analyzed for dissolved phosphorus and dissolved nitrogen to understand how trees can help reduce these concentrations in groundwater. So you can see here at the summit well, concentrations are much higher, 2.7, 3.35 for total nitrogen. And the mid-slope well concentrations are still higher. And the lowest slope well concentrations are much smaller, 0.03 and 0.09. That's sort of nitrate. As you see here, there is a difference. When you have trees, the concentration is 3 times smaller for nitrate compared to the grass buffer. When you have trees, concentration is again 3 times smaller for total nitrogen in the agroforestry area. So which shows these are cottonwood trees. Trees were planted in 2000. Study was conducted between 2016 and 2018. So as you see here, these fast-growing trees, then they are deep into the deeper soil. So they can remove those nitrate, as also denitrification can happen because trees add carbon to the soil. That is the food for microbes. They can denitrify water and remove nitrates from the water. So now I have explained about surface water, how agroforestry can help improve surface water. and the groundwater. There is another kind of water just below the soil surface. We have not studied that water. So we installed water sensors at 5, 10, 20, and 40 centimeter depth in the crop area and in the buffer area. So we have replicated study. This was conducted at the Greenlee Center. So 4 replications on each watershed for crop area, 6 replications for each watershed on the grass buffer and tree buffer. So these were installed in 2004. We monitored those water changes until 2021. And the sensors are now not working because they were in the field for a long period. So that's the moisture change at 5 centimeter depth. First figure shows the precipitation during the study period during year 2017. Then moisture at 5 centimeter, 10, 20, and 40 centimeter depth. So as you see here, there are several lines. The top line shows water content change in the crop area. Usually you plant corn or soybean in May, June, July. So until that time, there is no vegetation to remove water from the soil. So the soil water content is much higher in the crop area. That's the first line within a graph. And trees and grasses, they leaf out as soon as the temperature is right. So they are starting to remove water from the soil, maybe end of April or end of March or mid-April. So their tree water content is much lower. So the lowest line within each graph is the tree water content. So it maintained very low moisture content within the profile compared to the crop. Crop is highest water content, then perennial vegetation, as they leaf out, remove water, their water concentrations are much lower. So it continued for several years. As you see here, there are blue boxes. And if you look at the top graph, it says the rain event. So after a rain event, soil is recharged. Okay. So the crop area, tree area, buffer areas, every soil is recharged. Then again, the vegetation removes water from the profile, water content decreases, then again, after a rain event, it increases. So if you look at it carefully, look at the first graph, the first blue box, which shows the first top line is crop. Crop moisture content increased only by 10.35 to 0.45, very small amount. The lower line is for the tree area. That water content increased from 0.25 to 0.45, 0.2 increase, because there are better physical properties in those soil areas. High carbon content, lot of roots and microbial activity, those also help to improve the soil structure. That helps to improve much more water storage compared to the crop areas. As you know, crop areas, although it is minimum tillage, there is some soil disturbance, structure is damaged, so they don't store that much water compared to the buffer areas. This is about 2 centimeters of water storage, extra water storage due to tree buffers on the agroforestry watershed. So that means when it rains, those buffer areas can store 2 centimeters of rainwater compared to the crop area. So that can help reduce the runoff volume. So I just want to show during the recharge period. So we plant crops in May, April, May, then we harvest them in October. Then after October, actually hydrological cycle starts in October. So all the water content decreases during the growing period, then hydrological cycle that starts to recharge the soil, it starts in October. During the October month, there were several rain events totaling about 166 millimeters of rain. So look at this figure. The orange line is crop areas. As I explained to you, physical properties, carbon concentrations are not so good compared to the tree areas. Tree areas, better physical properties, lot of pores, infiltration is much higher carbon. When they recharge higher amount of water, even the lower depths. The summary is when you have tree buffers, they can store more runoff water in the buffer area. That means it reduces the runoff volume. So my first section about the provisional services, I explained about the water. Agroforestry can help supply different kinds of food. As you know, agroforestry buffers can have different vegetation, not just trees, nut producing trees, mushrooms, and different trees. So they can supply diversified food types for anybody. So we looked at corn soybean rotation, the watershed. We conducted 3 different studies. One was at the Greenlee Center. One was at the Russ Jones farm. It also had a LA cropping practice with 8 different silver maple trees. And the third one was conducted at the Bradford farm. So to look at what the trees do to corn or soybean yields. The left side of graph, your left side, uh, shows corn yields, how the corn yields change from buffer distance from the buffer. As you see here, corn yields are much, much lower. Then the second set of graphs shows soybean. Soybean yield was not affected by the buffer system because soybean adjusts to the moisture situation and competition. They shed extra flowers, extra seeds, and produce a certain amount of yield. So the soybean was not affected by trees. That means competition was minimum for soybean yields. However, corn was affected by the buffer end. The effect continues from the buffer end to about 5 or 15 meters. That depends on the rainfall of that year. So this study was conducted for 6 years. It's a corn soybean rotation, 3 corn years and 3 soybean years. So which shows soybean was not affected by the buffers, but corn was impacted by buffers because trees are competing for water and the shading effect. And the third study we conducted at the Bradford farm, it had riparian buffer and CRP grass, Conservation Reserve Program grass. Grass was planted in between the trees and the corn soybean. The impact was much lower because shading was not affecting crop yield because grass is shorter. So the idea is if you want to have agroforestry buffer, you can have plant CRP grasses in between the crop and tree areas. That way you get additional income and also reduction is much lower. So let me explain about the livestock industry. This study was conducted by Rob Columbach in 2009. He looked at forage production and cattle weights. So as you see here, those blue areas, the agroforestry system, because of the favorable moisture condition, reduced stress condition, produce pasture early in the spring. So that means you don't have to buy a lot of hay for cattle management. And also in the summer, production is much higher because shading and favorable conditions. And it also continues into the fall, which shows when you have an agroforestry system like silvopasture, trees within the grazing area, they can produce more hay. Farmers don't have to buy a lot of hay during the winter period. And the quality of the hay was also much better compared to the traditional grazing management. So he also looked at cattle weight gain and weight loss. So as you see, traditional farming system, cattle is exposed to sun. When you are driving around the area during hot summer, you might have noticed all the cattle go under a tree and stay there under a shade. So they need some stress reduction method. Okay, when you have trees in the farm, weight loss is much lower compared to traditional method 235 versus 205, and the weaning weight is much higher, 595 versus 650. During 2009, this translates to about $43. This is in 2009. Now it's about $64. That means you are planting few trees in the grazing area. You can provide shade, you can reduce the stress, then weight loss is reduced and weaning weight is much higher. So now I'm going to talk about the regulating services. The first one is flood control. So you may have heard during the last few weeks, there was a lot of flood in areas, North Carolina, South Carolina, damaging agriculture and everything. So this lower figure shows they looked at precipitation conditions from 1958 to 2012 and compared highest intensity 1-inch rainfall amounts. They have estimated 71% increase during that 55 years in the Northeast and even 5% increase in dry areas. So that causes a lot of damage. So Dr. Dwyer, he was a faculty at the School of Natural Resources. He was a silviculturist. He looked at the levee break. I don't know, some of you might remember 1993 flood. That plaque shows at the St. Louis Arch, they have put a plaque that shows the water level during 1993 flood. It was about 49.5 feet above the flood level. If you go to St. Louis Arch, just look for that plaque that shows the water level during 1993, August 1st. So he selected the 100-mile distance in the Missouri River. They looked at levee breaks. The bar graph shows if there is no riparian buffer, levee breaks are about 45. As you increase the number of, uh, uh, as you increase the width of the riparian buffer, if it is more than 300 feet, the levee break is much, much smaller, either 1 or 0 or 2. So which shows if you establish or maintain at least 300 feet riparian buffer, you can reduce the levee break. Levee break is not just a levee break. Then it deposits sand on your farming land. You can remove that sand tomorrow, but you don't know when is the next large rain event. So when you have trees, it intercepts water, rainwater, and it depends on the vegetation type. It transpires water. Cottonwood and willows are fast-growing trees. They transpire a lot of water because you produce high-volume tree species. They remove the water. That means strengthening the stream bank. And the graph shows what happens when you remove trees. What happens when you remove trees? You remove all the roots, right? Binding agent is gone. No carbon, no organic carbon. That means root strength decreases after you remove trees. Then the revegetation starts. With that root growth, carbon addition, strength increases. So that's what happens when you have a permanent riparian buffer condition. Stream banks are strengthened. So this is to show what happened. This is Cambridge, north of Marshall. It's about 95 miles northwest of Columbia. 1992, as you see here, that area, there's good vegetation. Sorry for the black and white image. These are Google images. In 1993 flood, if you look at the 1995, a lot of sand deposition in that area, white. Okay? So that means that farmer cannot use that land area for crop production. If there were buildings, the building would have gone. So in 2009 and 2012, nice vegetation. This is at Cambridge, about 95 miles northwest of Columbia. After this 1993 flood, Missouri Department of Conservation and Natural Resources bought about 80,000 acres of land, flood-prone area. They paid landowners, they acquired that land, so it was under riparian management since then. So trees have two different roles. They are physiological and physical. Physical means resistance to flow, roots, leaves, branches, fallen branches, tree stems. And the physiological, they can store some water, remove some water, transpiration. So that can help strengthen stream banks. So then the second one under the regulation is climate control and carbon sequestration. As you see here, trees have large roots and volume is large, bigger. They can deposit a lot of carbon into the deeper soils, and these can stay in the soil and also in the stem for longer periods. So we looked at the Greenlee Center Research Farm, we looked at carbon distribution about 5 or 6 times. In 2000, March, June 2006, June 2008, May 2020. So what we see here is changing carbon concentration. The first column, before any buffer establishment, average carbon concentration is 1.85, 1.88. Buffers are not established. The last number on the first column is 2.3. That means grass waterway. Grass waterways were established in 1990. So those are denser vegetations, all the nutrients, fertilizer, stores, accumulates in the grass waterways, better conditions. So they had higher carbon concentrations from the beginning. If you look at the last column, compare with March 2000 and May 2020, that was I had a PhD student, he's now a faculty at Panama University. He conducted that study. He looked at changes in carbon concentration. In the crop area, carbon increased from 1.85 to 1.94. It's only about 5% increase in carbon over the years. And the agroforestry carbon increase was about 16.5, 1.88 to 2.19. The rate of increase was much higher in the agroforestry, although grass waterway had higher concentrations because they have a better vegetation condition. Another study we conducted looking at carbon up to about 1 meter. I'm showing here about 45 meter. Crop areas always had very low carbon concentration. Look at the tree buffer area, 106 within the first 50 centimeter soil compared to 90 in the crop areas. And after we collected so much data, we wanted to write a review paper to understand carbon sequestration potential of the US. So you know a lot of silopast area, grazing areas, unmanaged forest, they can use for grazing. That means if you use 10% of the grazing areas, unmanaged forest, and if you establish riparian buffers on 3.5% of the 3.5 million miles of river length, you can increase the carbon concentration. As you see here, the carbon in those areas during using agroforestry can be increased up to about 600 tegagrams carbon per year. Carbon is very helpful. It can improve supporting services, regulating, provisioning, and cultural services. Let me explain this figure. The vertical line is available moisture content. Horizontal line is x-axis, carbon addition. Two lines within the graph, black lines, which shows permanent wilting point and the field capacity. That's the amount of water available for plants. Water between the permanent wilting point, below that, plants cannot absorb that water. So that's the water available there. The blue lines represent at 1% carbon. Soil has about 10% available water. At 1% carbon, that soil has about 10% available water. When you increase the carbon to 4%, it doubles. As you see here, blue lines almost double. So just increasing the carbon concentration in the soil, we can increase the amount of water stored in the soil. So this is a document from NRCS. If you increase the carbon percentage just by 1% on all agricultural soils, they can store 150 days of flow from Niagara Falls in those soils. So Zoma has done a study. He looked at globally. There are about 43% of the agricultural lands have at least 10% tree cover. And the tree cover has increased over the last 10 years. So those trees are contributing to a lot of carbon globally. And trees also help improve air quality. This study was conducted by Chung Ho Lin. He used a concentrated animal operations, K4 factory near Greenlee. So he planted 3 rows of trees around the K4, concentrated animal feeding operation. There are about 506 K4s in Missouri in 2009. So now the number must have gone up, and Iowa has much more higher K4s. So he planted 3 rows of trees around the animal operation, and he noticed greater reduction of ammonia, dust particles, and everything from coming to the air. So that means agroforestry can help improve air quality of different land use systems. If you touch a leaf along a road, you might notice dust and other material on leaves. So you do the same thing when you plant trees around a facility that helps improve air quality. Now the last section is about soil health. So this is a figure taken at 25 micrometer resolution. That is 40th of an millimeter. So you can see roots, animals, decayed boreholes, okay? I explained to you, a lot of people use, livestock industry use about 22 million pounds of antibiotics. So animals keep only about 30% of the antibiotics, 70% comes to the soil, low water. So we looked at 3 different soils from research farms to study what is the role of these soils in holding antibiotics. The gray lines represent agroforestry soil and grass buffer soils and this crop soils. As you see here, 2 different antibiotics were strongly held by agroforestry soils. It was high carbon concentration, high microbial activity, lot of organic material in those soils and diversified products. So they can strongly bind antibiotic and keep in the soil. So that's another activity when you have trees near the water body. But it depends on the tree species. Some species are much more effective. As you see here, the poplar, it can degrade antibiotics within about 100 hours. Switchgrass, it takes about 300 hours, which indicates when you have an agroforestry buffer, you need to have diversified vegetation, not just one species of trees. Several species of trees, several species of grasses. And if you are interested in generating income, some income generating plants. So we looked at soil properties, how it changes because of agroforestry. We collected soil samples and took to the University of Missouri X-ray machine, this human X-ray machine. That's about 200 micrometer resolution. That's 1/5 of a millimeter. So you can study some pores, not those tiny, tiny pores. So this is how it looks. You want to remember that we didn't disturb the soil to take bigger roots, because if you hit a root and if it shatters, that change the soil structure. So we didn't look at large roots. These are tiny roots that can be cut using that sampling equipment. As you see here, your right column, more black areas, that means more pores. So these can be studied using high resolution X-ray machine. For example, geology has a high resolution X-ray machine. They can study at 1 micrometer resolution. So when you plant trees, it improves soil aggregate stability. That means resistance to flow. You see the measuring cylinders, low aggregate stability, so it's crumple and get into the water bodies. And we also looked at soil thermal properties. If you have trees, some shading, some carbon, that means more thermal conductivity is much lower compared to red lines are for crop areas. As you see here, conductivity is much higher throughout the profile for crop areas. When you have perennial vegetation, thermal conductivity is much lower. That means they are creating a favorable buffer conditions due to shade, due to organic matter addition, roots and leaves in those buffer areas. And in terms of biodiversity, we looked at the red blocks show crop areas. Enzyme activity is so much lower. That means less organisms compared to tree area. And also this student did for his PhD work. He sent samples to a lab and look at microbial parameters. All the organisms are much higher in the perennial areas compared to crop areas. So I wouldn't have done all this work without the support from a lot of people, a lot of faculty, students, technicians. A lot of people helped me to complete this agroforestry research. Thank you, everybody. I also know I couldn't find some pictures of some people I missed. I remember about 12 different people. For example, Pekka Nygren, he's from Finland. I looked for him, social media and every place I didn't find his picture. So thank you for listening to my talk. As you see here, agroforestry can help improve ecosystem services. Do you have any questions?
We're going to take some questions.
In the one where you showed the difference between grass waterway, agroforestry, croplands regarding the particular parameter, the grass waterway was higher than the others. Was there a factor of time of how long it had been established that was different, or was that the same across those areas?
The topography is about 9% slope on this area, the agroforestry watershed. Grass waterways are usually located near the exit point. That's the lowest landscape position. So anything that eroded water that can carry fine particles, fertilizer, everything is deposited here. Waterways were established in 1990 and a difference dense grass compared to the buffer area. So that's why it had higher concentration of carbon, microbial activities, everything, better soil properties. Thank you for the question.
We have time for just one more question before we shift gears. And I want to also mention, if there are questions, lingering questions you have online or here in person, you can add those. There's a tab for lingering questions in the resource exchange on the symposium page.
I'll follow up on the last question. You planted those grass waterways in 1990, correct? So that was a long time ago.
Yeah.
And what were the grass species?
Fescue.
Okay, fescue. So as time has gone on, there's a big increase in the interest in planting more native grasses or native grass orb mixes in those waterways. Is your more recent research moving in that direction?
Since this is a long-term study,
I know then.
Yeah, we don't want to change the configuration. So that can affect.
Now, as you're moving forward in doing these sorts of studies, are you starting to shift those waterway buffer species to more native or grasses or native forb mixes? Are you doing any work to evaluate that
We
for the
looked
future?
at some rainfall simulation studied at the Bradford Center, looking at native versus hedge versus tall fescue. As I showed here, Chung Ho Lin study. it showed improvement, but I don't know what will happen because I'm planning to retire within few months.
Yeah, the next person who attempts to fill Dr. Udawatta's shoes will hopefully take that on. Thank you, Dr. Udawatta, for your presentation and for your work.